All right, so let's talk about limiting factors, population densities, and survivorship. That's what these notes are all about. Okay, so first step is talking about distributions and densities of populations. Population density is nothing more than a formula. You count the number of individuals that are in a population and divide by how much square footage there is of where they're living. So it might be square meters, it might be square centimeters, it could be square miles. Just depends on how big the area that population lives in, their ecosystem that they're calculating that from. All right, so just an equation. Populations, they live in a very noticeable pattern. Okay, so we can tell exactly how they live. For instance, fish that live in the ocean, we know that they have schools, right? You've heard that before. So we call that clumped dispersion. That's nothing more than they have like these clusters or these schools where they live. Uniform dispersion is where there's very consistent amount of room between them. You'll see a lot of this with nesting. You can see how there's very, very specific amount of room. They've got their space and they're not going to let another bird come into their space. So that's uniform. You can see it's definitely very uniform. The last one is random, and that's just where you live where your resources are, and it happens to be here today and there tomorrow. So it's very random, and you can see the sloth hanging from the tree. Good example of that randomness. So that is population dispersion. Survivorship. What is survivorship? Well, it's nothing more than a formula we calculate, a lot like how we calculate our grades for our tests. The amount you got right divided by the total that was available. Okay, and you get your percentage. Well, survivorship is nothing more than that. It's the amount of deaths that you have in a population divided by the total population that are available. So there you have it, survivorship. And you can put it in graph terms. And if we look at survivorship, you can see that there's three basic types of survivorship graphs and predictable curves that come out of that. If you are considered a type 1 organism with a type 1 survivorship, you're going to be in the category like what we are, humans. We nurture our young, we care for them, and we have good resources, so we tend to live long years. So you can see from the graph, the percentage of the life expectancy, we live long time. Somewhere around 70 to 100 is where we start seeing our individuals typically aging and then dying off. Okay, elephants fall in that same category. Type 2 are organisms that have, basically for every birth that they have, there's a death that happens. So they have equal. So you would expect that if there's that direct relationship, you would get a straight line, which you do. Okay, and organisms that come in this category are like your alligators and your birds. So it's your reptiles and your birds and so forth. Type 3, let's have as many babies as we possibly can and hope that we get as many through to adulthood to reproduce for the next generation. And that's type 3 survivorship. So they have a very high birth rate and a very high mortality rate. And that's like plants, insects all fall in that category, so your invertebrates. And you can see not going to live very long, going to have death fairly quickly. Okay, so that is your three types of survivorships. What are the four factors that make a population's predictable in size? Well, the four factors are how much immigration is going in and out of the population, so immigration, emigration, and then how many births and how many deaths. And scientists can study all this and obtain all that data in field research and then make predictions on that population based on that. So very, very predictable how populations will respond to their environments and their resources. We looked at the difference between an exponential growth curve and a logistics growth curve during bell ringer today. So this should just review what is exponential growth, rapid growth. You can see 2 very quickly become 4, and 4 becomes 16, and 16 becomes 256. So you get that quick rapid growth. Okay, and that's called the J curve sometimes. Rabbits, bacteria, even elephants, believe it or not, fall in that category of having reproduction. Then the other one is logistics growth, which is very similar to exponential growth. You can see that there's an exponential component here, but at some point the population starts to kind of slow down a little bit and taper off, where exponential would just keep going up, and then eventually the population hits what's basically like a cap, where they can't grow anymore because maybe their resources are not available or whatever. Something has caused the population to cap, so it will not grow. So their growth rate basically equals 0, and they flatline here. Okay, they basically plateau. And that's the S curve, and you can see how it kind of makes the letter S there. It's kind of stretched out, but it works. And two other vocabulary words that are kind of associated with this whole plotting of populations is the carrying capacity and a population crash. Carrying capacity is when it's that plateauing point. It's where the growth rate of growth equals 0. So there's no more growth in the population, and something has caused that population to stop growing. Population crash is if they hit that plateau and then they see a huge decrease in the amount of organisms. That's a crash in the population numbers. And one of the things you definitely want to make sure you're confident with is reading and interpreting graphs and data charts and so forth, because there'll be a lot during this unit. So here's one where we've got fish kills, the amount of fish, or a number of fish that were killed in the event, and then we've got rainfall in inches, and you can see then we also are calculating that over the months of the year. So we've got a 1-year span. So typically temperatures colder in the winter months, then they warm up in the spring, then they get really hot in the summer, and then of course they cool down again and then get cool. So that's your typical calendar year of seasons. You can see the fish kill, which is the blue bars. You can see not huge amounts here, but wow, in June and July and August, those numbers were really crazy, and then of course low again in the fall months and leading into winter. Well, one of the things scientists do is study why we have this huge fish kill. Well, if they also then correlate that to the amount of rainfall that came, you can see in our spring we had a lot of rainfall, and then we had basically little to no rainfall. It was in the deficit category, in which case ponds, lakes, streams, all that stuff's going to start to dry up. And where do the fish live? In the ponds, lakes, and streams. So you can see why they were dying off then. If we had all this evaporation from the temperatures being warmer and we had no rainfall or little rainfall, you can see then, why there was that change there. So there's a direct correlation with that. So anyway, population crash. We had these great numbers, and then bam, the population crashed, right? Numbers just totally went down. The last thing we need to talk about is population density dependent and density independent limiting factors. Populations are capped or limited, and it falls into the two categories. If it's considered a dependent limiting factor, it's happening within the population and to the population directly from within that population. Okay, like predators, like we had in our game today. The wolf population came in and directly impacted that population, and they were dependent on the density of that population. Competition, when your density is up, you got more competition for your resources, and eventually your resources are going to get used up, and then you go into a real competition situation. So competition is a limiting factor from within that population. Also parasitism and disease. When you have those dense numbers, then you've got organisms living in a very, in a confined space with lots more organisms. You can imagine that disease would definitely go up. Okay? So those are your density dependent. Flip side of that is the independent limiting factors, and these basically they just happen because they happen, and the population has little to no control over that. So things like unusual weather, like thunderstorms or heavy rainfalls or super hot summers or super cold winters, that's unusual, weather depending on where they live. Natural disasters, tornadoes, floods, forest fires, those kind of natural disasters. And then, of course, human activity. If we come in and we decide to just clear out a wooded area so that we can build a subdivision, we have an impact on any organisms that are living in that area. We've basically kicked them out. So you can imagine that would affect their population density as well. So those are your notes for today. Be prepared to possibly take a quiz tomorrow, and I will see you then.